Okay. Good morning. Yeah, here we come. The last lecture of ECE 350. Now, in terms of announcements, I have a couple. So for the last quiz, which will be similar to all the other quizzes, there shouldn't be any difference. We will release it a few days before the announced deadline. So you'll have about 2 or 3 days to complete the quiz. Those of you who want to do the quiz. That's that. With lab 4, as I announced, I confirmed with the university that we can indeed have demos, but we will have to wait for all students to do their exams. So it will be after your last final exam. So after that, we'll have a demo week for all lab 4 submissions. Yeah, that's pretty much it. Now, in today's lecture, hopefully I'll walk through the lectures on file system, and if we have time, then I'll talk about file system reliability. If not, then I'll include I'll include links to the last term's lecture on reliability. Probably I'll have to also include links to last term's file systems as well. There are a couple of file systems that I probably won't be able to cover today. Okay, if there are no questions, then I guess I can get started. Okay, so yeah, we were talking about file systems. Now, when you access files on your machine, give me a sec. Yeah. So when you access files in your machine, in storage, you could either have sequential accesses, like let's say you're reading a big file, and let's assume that the entire file is put on sequential sectors on your device. So you're saying, I mean, I don't care about the device. Let's say you're reading the file. You say from byte X of this file to byte Y of this file. Give that to me. So you're going through logical blocks in your file system. That's a sequential access. You might actually want random accesses. You want to seek to a position inside your file. Let's say, give me byte number 1024 or whatever. So those are random accesses. Now, for the first one, it's very common, and it actually constitutes most of your accesses in your file system. Random access is still common. It happens not as frequently as sequential accesses, but these are also important. Let's say you want, you have a file that you store all page tables, for example, or you have a file that you store all migrated pages, and you want a particular page to read, or you want a particular page table to read. So you have to be able to go to that particular object inside that file that you want. That would be random access. You might also want content-based accesses. You want to go through a directory and then read any file with a given name, for example. So that basically requires some metadata searching and then bringing you the content. It's very similar to what databases have. And many operating systems, including Windows or Mac OS, do things like that, where you, for instance, you use the search, you type something, it indexes all the files, and then you just get what you want. Okay. So from the user perspective, users of the system create, edit, modify, delete files, and rely on the file system to just store them for them and make those requests happen. So if a user asks for bytes 2 to 12 of a particular file, then the file system should know the mapping from byte 2 to byte 12 in the file system. So file system, as I said, the granularity is blocks. So file system should know which block or which blocks, depending on the size of the block, should be fetched. So this is the job of the operating system, to do this mapping from bytes that the user wants to the blocks that operating system or file system knows about. And once you know which blocks you want, you also should know that you have to go to the storage and then tell the storage, give me this block to that block. Now, what if you want to write from byte 2 to 12? The same thing. You should know which block you're concerned, or which blocks. You fetch that block, you modify that block, and then you save that entire block. So from the user's perspective, they're just writing few bytes, 10 bytes, let's say, from byte 2 to 12 or 11. But from the operating system's point of view, everything is in the granularity of blocks. So, and if a block is like, let's say, 4 kilobytes, then the file system is really reading an entire 4 kilobyte of data, because again, that's the granularity. Now, from user's perspective, you're working with get character or put character, but from the operating system's point of view, you might be actually working with 4 kilobyte file, 4 kilobyte data at that exact same time. Now, there is another perspective that we have to be aware of, and that's the perspective of the device under the hood. Now, operating systems is dealing with blocks, but these blocks might themselves be translated to sectors on the device, and then the device knows how to deal with that. So physical storage works with sectors. That's the entire point of this slide. Operating system works with blocks, and users might just care about few bytes. Now, there was this study years ago from Microsoft. They looked at the usage of files in typical file systems. They studied, it was a 5-year study that surveyed files and file systems to see how users usually use file systems. And this study is actually important because it gives us perspective on what to expect, what are the trends in accesses. Now, again, why is this important? Because if we know how files are accessed usually, we can focus on optimizing for the case that is very common. So if we particularly identify a case that is very common, we might want to optimize that common case so that most of our users are happy. Now, this is a little bit dangerous because you shouldn't just focus on the common cases, because if you optimize for the common case and then you screw things up for uncommon things, which as I will mention, is sort of what Unix file systems did at some point, then two things happen. First of all, well, you screw up the uncommon case, and that uncommon case might be a common case for a particular user, so they will be frustrated with your system. The second thing is that you could actually shift your user's usage pattern. So if I'm a user of a system and I realize that my system is super fast with small files, for example, it can very efficiently store them, modify them. But whenever I'm dealing with big files, the system is sluggish, is slow, then I might decide to always have a small files. This actually happened to me. It wasn't about a file system, it was about an application. So I was working with Word, Microsoft Word, and then whenever the document was like, more than a few hundreds of pages, then it would just crash all the time. So I had to eventually figure out that I have to work with smaller files. I was doing really a lot of modifications to the entire file, like select all, change the color, change the style, do this, do that, and then the system would just crash. So that changed my pattern. The way that the software was designed changed my usage pattern. Now, if somebody studies my usage pattern, they might think that, oh, all I have are small files. Whereas in reality, I actually had a big file, but because the system sucked, I had to work with the small files. And that actually could happen, and I bet it's happening. So we'll see. We'll see when we talk about Unix file system. If I guess I'm not gonna, but when you watch the video, you will see that I mentioned how Unix was just designed efficiently for small files, and that might have changed the usage pattern of users. Okay, so this is the first important graph in this study. So this is like on the x-axis, you have file size, how big a file is. And then on the y-axis, you have frequency of having those files. How many of those files there are in the system. And as you can see, most of the files in your system are here, like between 2 kilobyte to 32 kilobyte. And then you can actually see the curves from different years, from 2000 to 2004. And as you can see, it's kind of like this. There is a peak here around 2K to 3K, and this curve slightly has shifted, but not by much, right? So it has remained the same, sort of. It's the curve is concentrating more and more. The variance is going down, and you could imagine a pattern like this to happen, like most of your files in the system being really small. Then oh, this is another graph that is important. So again, here on the y-axis, on the x-axis, you have file size, the size of your file, and on the y-axis, you have the used space normalized over all the file systems that they studied. What this means is, if I look at all the files that have 32 kilobyte size, I might have a lot of them, right? let's say I have millions of them. Not million, I don't exactly know how much, but you can actually calculate looking at this graph. So these are megabytes. This tells me that for 2004, all the files that had size 32 kilobyte collectively, in average, occupied about 200 megabyte. So this makes sense. I have really a lot of 32 kilobyte files, but each one of them is 32 kilobyte. So if I multiply the number of these files times the size of them, I get a point here. Now, if I look at a file that is 1 gigabyte, I might only have, so this figure basically shows that in 2000 and in year 2000, this is probably 100 megabyte, right? The file is 1 gigabyte. Having it occupy 100 megabyte, this means that in 10 file systems that they studied, only one of them had a 1 gigabyte file. So the frequency of having a 1 gigabyte file was 10%. Now 10% times 1 gigabyte, that's basically 100 megabyte. You get a point here. Now, as you can see, moving to 2004, this is actually getting close to actually 1 gigabyte. This tells you that every file system at that point had at least one file which was 1 gigabyte. So now looking at this, it feels like most of the space is occupied by files that are between 2 megabyte and 16 megabyte. So these are two concepts, right? The first one was which files do we have more frequently? The answer was around 32 kilobyte files. You have a lot of those, but you have a lot of them, but because the file is really small, they don't occupy much. Now, on the other hand, files between 2 to 16 megabytes seems to occupy most of your space. And as the years passed by, this actually peaked. It slightly moved from 2 to 16, right? But you still have it here at peak. What is interesting is that you kind of like started having another peak as well. So two peaks sort of showed up in this graph. So we are seeing that really big files started to occupy space as well. You have really few of them, but those few are so big that you have to pay attention to them because they're consuming a lot of space. So these are two important graphs from this study. Now the takeaways are first of all, most of the files seem to be really small files. Second observation is you have very few large files, but they occupy most of your storage space. And these two facts shouldn't be in opposite direction of each other. So they're actually in line. Now, as I said, you should be aware that this is a good study to consider. Maybe we can, optimize for, now that we know that most of the files are small files, maybe we can optimize for that, but we shouldn't actually screw up big files. Because if you do, then you might actually be screwing up a particular user because they all have like big files, right? As I mean, those of you who work with Unix, you should know, right? Whenever you have big files, the system actually struggles to, or used to be. Maybe things have changed. I haven't had a Unix system. I mean, Mac is kind of like Unix based, but yeah, but for at least now 2 or 3 years, I haven't worked with. I mean, I still have a Linux system for my research, but not for daily usage. So I don't exactly know where it is right now, but things used to be really sluggish with big files. Okay, so the concept of directory now. We kind of like covered concept of files, which is basically, but from the user's perspective, you know, a collection of bytes. From the file system's perspective, collection of blocks. From the storage perspective, collection of sectors. Now, what is a directory? Now, directory is basically a human readable name, a list of human readable names for each file or directory. So it's kind of like it has a recursive nature and recursive definition as well because of that nature. So you have folders that contain files and other folders. So folder is kind of like a name that I believe Windows systems introduced. It's similar to directories, right? The concept. Now, I think there is a distinction between folders and directories when it comes to Windows operating systems. I think the concept of folder has something to do with the graphical user interface, what is shown to you. But nevertheless, I think in day-to-day conversations that we have, we use them interchangeably, folders and directories, especially like in Unix systems. Okay, so any system has a root. Any Unix system has a root directory. So if you consider a directory as a tree, which basically has elements that are directories themselves or files. So all the leaves of this tree are files, and all intermediate nodes are directories. So the root of this tree, we call it root. Quite you know, it's an unshocking fact. In Unix, that's how we show it. Now, a path is, we have two types of path. We have absolute path and we have relative path. An absolute path is from the root to the file or the directory that you're interested in. This is an example. From root directory, go to home directory, go to SMZ directory, and then find the foo.txt file. Now, if you are in a directory, you could use a relative path. So from where you are, let's say if you're in the home directory and you want to address foo.txt, you could just say, go to SMZ directory and then foo.txt. So you don't start from the root. So it's just a relative path. Now, in file systems, you have two types of links. Hopefully, you know these from 252, but just a reminder. So you have hard links and you have soft links. So with hard links, you could have a single file and then two paths, two absolute paths for the same file means that you have a link, meaning that two directories, for example, are pointing to the same file. So different path, user lib foo or user lib7 foo, both of them pointing to this foo file. Now, if it is a hard link, if let's say this was the original path and then you created this path as well, so this became a second path, then it's a hard path. Now, if you delete the original path, so if you say delete root user lib7 foo, all that happens in your system is that this link will be deleted. The file doesn't get deleted because it has another pointer. So the file remains and this other link stays in place. Now compare that to soft links. Now if you have soft links and you delete the original link, then the file will be deleted. And you have a dangling pointer here pointing to nothing. Now, if you want to use this, if you want to create links in Unix systems, ln is the command to use. It creates a link. This is passed to the file and then passed to the link, the link that you want to create. Now, if you want it to be a soft link, then you just include a -s as an input to ln, and that tells ln to create a soft link. Now, okay, so where are we storing directories? Everything in file system, again, unshockingly, is stored in files. So a directory is also stored in files. That's important. Now, in essence, you can work with directories by just working with files, right? You can open a directory or create a directory by just creating a file and putting some metadata inside it to indicate that this is a directory. That would be requiring everyone to know all the metadata that goes to the file. You want to basically factor that out. So you have indeed system calls that are designed to just work with directories instead of just opening and reading and writing to particular files for directories. You can create a directory. You can by make directory, or you can link. So these are the operations that actually modify the directory transparently from the user. User doesn't need to know what is written or read from the directory files. Sometimes, like, you can open a directory in a Unix system by a text editor and see what's in it. Usually for me, these happen when I'm using VIM and I'm just making a mistake. Instead of my file, I open a directory, and then I see like bunch of data written in that file, which sometimes are not readable, the characters, because of the structure of the file. But anyways, the point being that the directory itself is a file that you can modify, read, and write to. What happens when you delete a file in your file system? Well, your file system has to have a counter for each file to count how many links there are. As we just saw, if you have a file with hard link and then you remove one of them, then the other one should survive. And then the same concept as these system calls, libc supports functions that are created to exactly modify directories. Instead of, again, going with usual calls to modify and alter files, you can just work with directories using these functions that are provided to you by the system library to work with the directories. Hopefully you've seen some of these in 252. I'm not quite sure. Now, the other concept of file system is volume. So first was file, the second was directory, and now the third one is the volume. Now, volume is a set of physical storage resources that indicate a single logical storage device. So basically, under the hood and inside your device, the data is stored somewhere on a physical device. Now, each file system, each instance of file system can manage files and directories for a single volume. So a single volume, it could contain multiple storage devices. All of them constitute a volume, and then on top of the volume, you install your file system. So each file system manages a single volume. That doesn't mean that that file system is managing a single device, because that volume could have multiple devices. But you could mount multiple volumes to a single file system as a point of entry. Now, this is how you get that recursive definition again. So you could have one file system managing a volume, and then you have another file system that manages another volume. Now you can mount this second one to the first one and give it an entry. So every time that the parent file system wants to write to a file in the second file system, it goes through the path, it reaches the mounting point, and then it just gives everything it has to the second file system, and the second file system takes care of writing or reading or modifying the files in the second file system. Here is an example. Let's say you have a flash drive, and you have installed a file system on it. So this is like one device, one volume, and then one file system. So this is your file system on this device. Now, when you connect your device, your driver, to your laptop has its own file system or two. Let's say one. You could create a file and then mount your device, your second file system, to this file. So this becomes the mounting point or the mount point. Now, let's say Alice has this USB drive, USB volume connected to her laptop, and she wants to write to this particular file. Now this file has a path, right? From the root of Alice's file system, it goes to this file. If Alice, let's say, wants to read that file, Alice's file system, the original file system, comes to this mount point, realizes that this is a mount point. So from here, it calls the other file system with the relative path from here, which then would constitute as a absolute path for the second file system. So the second file system could go and read that file, bring it back, hand it over to the first file system, and then shown to Alice. If you now get this USB drive and connect it to Bob's system, now Bob could have another directory or another file as a mount point. So in these two systems, the same file could get different paths, but the way it works is the same, right? The original file system handles all the data all the way to the mount point, and then from the mount point, the second file system takes over and manages the data movement. Okay, so that's that. So that's the introduction to elements of file system. Now, where are we going with file system? What is the goal for file system? Now, the goal for file system was what we said at the beginning. We want a permanent storage. We also want human readable names for them. Now, all starts with names. Now you have a directory that sits here, takes your human readable name and spits out a file number. So that's the first thing that a file system should do. Get a file name, spit out file number. Now, this file number, if I have my file number, I have to go to a data structure, which in Unix file systems, we call it index structure. So I get the file number, I go through my structures, these are my metadata inside my file system, and from here I find storage blocks for my file. And once I have the storage blocks, I can just from here call the driver of my storage and ask it to bring me the data related to this storage block, or write to that particular storage block. Okay, so let's say, we want to have this naming data. So our directory should get a human readable name and spit out a file number. So this tells me that inside my directory, I should have these mappings from file names to file numbers, because that's precisely what the directory should be doing, right? It should get a file name and then spit out a file number. So that's basically what they store. So if you look at a directory, in essence, it should tell you that this SE350 directory, which, as I said, is itself a file, has a file number 739 in this example. Directory ECE350, which itself is a file, has a file number 924. And this foo.txt file has number 158 as its file number. So that's all we need, right? If our directories store these pairs, I can traverse them and find my file number. So usually, let's say you have from the root, you have an address, human readable address. Let's say we're looking for home, SMZ, and foo.txt. So I look at home. In my root directory, I find the file number. Let's say magically I can now read that file number, which we'll talk about next. How we can access files if we have file number. But for now, assume that we have figured that out. So now that I have this file number 119, I can go and read this file, which is my home directory. Then I traverse it for SMZ. Now again, I find that SMZ file is 110. Again, assume that we can read that. Once I read that, now I'm looking for foo.txt. So I traverse this file, I look for foo.txt, and I find the file number. And eventually, again, I have a file number. Assume that I can read it. I read the file number, and now I have the file that I wanted. At this point, this should give me a bunch of blocks, right, that I have stored in this file. And then I should be able to give these blocks to the device driver, to my storage driver, and it has to figure it out with whatever device understands talking about, right? Sectors and stuff. Okay, so that's the easy part, actually, getting from human readable names to file numbers. Even for this easy thing, which has a recursive kind of dynamics to it, how do we store this? How do we store this data inside is kind of challenging, and there are different ways to store this pair in your device. So one is basically a simple linked list structure inside directories, right? So basically just a pair of, it's just a linked list, right? So if I open this SMZ file, this is what I see. Name, file number, next element. Just a linked list, right? This is basically myself, file 110, dot is itself, 2 dots is the parent directory, home directory. If I go back in the example, you see the home directory was 119. So the home directory is 119. Then it has a pointer to next. Next one is SE, and it has this number. Next one is ECE, it has this number. Once we're done with folders or directories, we put some space. So this space will be occupied later on with if we add other directories. And then at some point we start putting our actual files. So this is basically the next, and then it's foo.txt with number 158, and then it's pointing to the end of the file. So basically a very simple linked list. We traverse it to find file numbers. Now, this is simple, so that's the plus side. It's simple, low overhead in implementing it because it's simple, but it becomes really sluggish if you have directories with thousands and thousands of files in them. So in essence, you will end up having to traverse your entire linked list if you have a big file, right? Let's say you have a file with thousands of small files in it, or thousands of directories, and then each one of those directories has thousands of directories. So basically, every time you go to search, you have to go through the entire linked list if you're not lucky. And that's basically a lot of overhead that we want to avoid. Now, as always, how do you improve on linked list? You use tree structure, right? That's basically what you do, and that's basically what is happening in modern file systems. In many of them, Linux, Microsoft, and NTFS, Oracle. So they usually for storing this pair of file name and file number, they have a tree structure usually, and it's usually B plus tree. Right now, I'm not going to go deep into this, but as you can see, having this tree structure actually helps you with finding your file, because now the traverse time is reduced to log n instead of n, and that's how you save overhead. In particular, this time, like this particular example, you hash the name of your file that gives you a number, and you use this number to traverse your tree. So each file has now a hash number, name, and then file number. So 3 elements. If you compare this with the linked list, you still had 3 elements. You had name, number, and then next, right? Here you have name, number, and hash number. So hash number comes top, then name, and then the number. Now you hash at the beginning when you're searching for a file, you hash that file name to a number, and then this number is your key to find this file. The way B plus tree, for those of you who are familiar with it, is that you have you divide it, you compare your key with each element. If it is less, so if it is less than the number, you go to the left side. If it is more than the number, you go to the right side. In this case, 30 is less, so I'm traversing this one. Again, 30 is less, I traverse left. Now 15, I'm comparing 30 to 50. Okay, it's more. I traverse right. 30, I go here and I eventually find my data. Okay. So it's now, if you look, like if you go deeper into how, because eventually everything is going to go to a file, so you have a flat representation. Here is how you can do that, right? You can, this is basically your directory. You have the name and the number, right? Each name has a number. So this would be the directory entries here. You put all of them here in sort of like you just list them, all of them. And then at some point you start to store your B+3 metadata. So you traverse this, and then each one of them has a link to these guys. So this basically becomes your tree, and these are your leaves, right? So that's how you implement them. So you allocate a region, basically the end of your file, to store metadata about your B+ tree, and then you store all the leaves at the beginning, and then each one of those trees is going to have a pointer to these leaves. That's how it works. Okay. Now that we took care of this first portion, which is file number to, sorry, from file names to file numbers, now let's go a little bit deeper to see what we're going to do with once we have the file number. Now that I have file number for my particular file, what am I going to do with it? How am I going to find all the blocks that are associated with it? Now, that's basically the hard part. Not hard part, but that's the meat of file system. Basically finding data for each particular file. You have to have some sort of notion of indexing structure. You have to index your files based on their number. You have to have some notion of index granularity, which basically tells you basically how big your block sizes should be. How are you going to manage free space? Which blocks are used by files and which blocks aren't used? How is this managed? How are you managing locality? Locality is was really important with magnetic disks, really important. It's still important with flash drives, flash storage devices, because as you just saw, like for instance, for writing, if it is sequential or not, it has consequences, but less important. And I would imagine locality probably wouldn't be that important anyways in future. I don't know. I mean, it will depend on the next technology, but it was definitely really important with magnetic disks because of all the physical components. So you really wanted your blocks to be written on sequential sectors to get the highest performance. So it was really important for the file system to take care of where and on which sectors each block should be stored. Again, it's getting less and less important. At some point, I mean, with your Flash, you have this Flash translation layer that completely hides what is underneath from the operating system, right? By just where leveling and moving around pages, each operating system has no idea where the pages are, right, on the device. Operating system cares about virtual pages, but then doesn't know where each virtual page is mapped to physical pages. So again, then it's less important locality, right? You still probably want to have your files getting sequence of virtual pages, but then you don't really know how those virtual pages are mapped to physical pages on your flash disk. With magnetic disk, you definitely want for your sequential blocks to get sequential sector numbers. And if you know the sector numbers, you probably know where exactly on the disk they are, because there is less transparency, more transparency with magnetic disks than flash. And eventually, the one topic that we probably won't get to talk much about is reliability. So at the end of the day, you wanted this data to be persistent. And as you will see soon, you have seen some of it, we are forced to have metadata for our files. Already we saw with finding human readable names and file numbers, we had to have some notion of metadata. It will be even more to find blocks. Now, that metadata itself has to be stored on the storage device. So we're using the storage device for storing the actual data from our users and also metadata. Now, this is important when it comes to reliability, because with reliability, you shouldn't just focus on users' data. You also have to make your metadata reliable, because let's say your user does a bunch of, operations, file operations, maybe deletes one file or maybe copies a portion of a file to another file and then renames that file and then deletes the original file and then, duplicates that file. So set of, transactions or set of operations on the file system. If your system crashes and you haven't written that data back to your storage, then it terminates in the middle of all these operations. And each one of these operations, let's say you copy, and that copy itself might mean micro operations for file system. It's like a copy for like big picture, but it's a bunch of micro operations for file system. For example, bring that data, then write it, then modify the metadata for that new file, then write that to the disk, and then maybe update when that data was modified, who's the owner of that. So there are a bunch of micro operations for each big operation. And if your system crashes in the middle, then you lose all that data. So although you have your user's data on storage device, file system is corrupted, so you can't find that data anymore. And the entire reliability guarantees of your system is in the air. So in order for this reliability to really work, sometimes you need to also take care of your own data and make them reliable as well. This is a topic that is highly focused in database systems, actually. But you can find origins for it in operating systems as well. Okay, so how much left? Okay, I have 25 minutes. Let's see how we can proceed. So coming back to what we were talking about, at this point, we want to talk about this index in a structure where, given a file number, I can find blocks for my file. So the simplest file system that usually is talked to or is talked about is FAT file system. It's file allocation table file system. It's one of the first ones and one of the simplest ones to implement. Now let's set the stage. Your operating system divides the available storage to itself to blocks. So that's the granularity of file system again, blocks. So you have certain blocks in your storage. Now each block gets a corresponding FAT entry. So FAT entry 31 is representing the storage block 31. Sorry, actually this is a file name, but you get the idea. So any FAT entry has a corresponding storage block in it. Now, in order for the file system to store files, if a file index, if the file number is 31 or whatever, yeah, I think it's in this example, if your file is 31. Actually, before going there, let me talk a little bit about it. So this was introduced in 1977, initially used for floppy disks. I don't know if any of you have seen any, but I remember them pretty clearly. So it was widely used. It is still widely used for its simplicity, basically. Many of the SSD cards, many of flash drivers are FAT, and it's supported across the board. So even real-time operating systems like FreeRTOS or ARM real-time system or Linux real-time system, they support FAT. Microsoft file systems, Microsoft operating systems support FAT. Linux file systems support FAT. There are variations like FAT32, FAT16, or other variations, but it's very widely used. So now, going back to what it's supposed to do, all I want is I have a file number. I want blocks. How do I do that? Well, if you have file number, go to the element for that. So file number is 31. Go to your FAT table, entry 31. And that basically tells you the file block that you have. Basically, block 31 is yours. Now, usually your file has more than one block. How do you do that? Well, each FAT entry will have a next pointer. So where is the next block of this file? Maybe in this example, the next block is the next block 32. And then maybe the next block is block, I don't know, 60 something or 70 something. So you basically create a linked list of these FAT entries. And each one of them, if they're used for file 31, meaning that they have a back pointer, or you can trace them back to this initial element, then all of them are allocated to file 31. Now, if you have, so let's talk a little bit about this FAT entry. So, so this, sometimes you say FAT table, but table is there, so it's file allocation table, but nevertheless people use it. So FAT table has these FAT entries. So there is one FAT entry per storage block, as I mentioned. Each entry is a 32-bit block. Sorry, a 32-bit element. So so that's the size of each entry, and then the file number is basically the index of the first entry, right? The first entry is file number and also the file block, corresponding first block for this file. Now, if you need block 2 of file 31, then you traverse this linked list, you find it, you find the corresponding block, you can read that block. Now, well, the first one is the file number. So these are the properties of the fat file system. File number is index of root of the root block of your file, as I have said 10 times so far. Now, you want to maintain a list of all free entries. So these are the entries, these are the fat entries that are not used for any file. You always have to maintain a list of them. You don't need any ordering for them. You just need a list. Now, let's say now I want to create another file. So if I want to create another file, sorry, if I want to expand my file, so if I want to write something to the end of my file, I can just pick one of these free ones and create a link to that to expand my file. Now, if I want to create a new file, I can find one of these free elements. The one that I pick is the important one. If it is a new file that I'm creating, because the block that I find will identify the number that this file is going to get. So if I pick block 63 here to be the first block of my file, that means that I have to give my file the number 63, because as I said, the first block is basically your file number. And then I create my linked list going forward. Now, where do I store fat? Basically, again, on the disk. You can cache it in memory so that you don't need to, keep going to the storage every time you want to traverse. What happens when you format your disk? All you need to do is to zero all of these blocks, right? So you write 0 to your blocks, and then you just make all your fat entries free. That's it. That's basically formatting your disk. What happens if you want to just do a quick format, if you've seen it? With quick format, you don't write 0 to your storage. You just make all those fat entries to free. You just mark them to be free. That's it. You don't go back to the disk and set 0. So what is the most significant advantage? Well, it's simple. It's easy to find free blocks because you always have a list of them. It's easy to append a file. It's easy to delete a file. And when I say it's easy, meaning that implementing this is easy, right? It's just you are traversing a linked list. Now, what are the disadvantages? Well, if you need a random access to a big file, then you might actually have to traverse the entire linked list of blocks, right? Let's say I want to read the last block of my file. Now, in order for me to find out which actual storage block that is, I have to go to my fat entry, the initial one. If it is, let's say, file 5, I go to fat entry number 5. I start traversing the linked list to find the appropriate block that I'm interested in. And then I look at the index of that entry to find the associated block. And that could take a lot of time if I have really big files. So basically, searching is order n, and n is basically the size of the file. It has poor locality. So as you start, so initially maybe you can, use sequential blocks in your sequential fat entries to create your file. But then as you start modifying your files, delete one and then create another one, delete particular block in your file, you start having these, the exact same problem we had, this fragmentation. And then new files that are created have to be, jumped, have to use blocks that are not necessarily sequential. So if then you use a magnetic disk to store your data, then your blocks are going to be scattered over the disk on different tracks. And this is really bad. So those of you who, I remember this. I had a Windows system that used FAT, and it exactly was a magnetic disk. And after months of using your system, 2 months, depending on your usage, they had this graphical interface that you could see your storage, and each block had a different color, and different colors were associated with different files. And you could see that like it was like a rainbow, like all the colors were just scattered all over the disk. And then it had this defragmentation option that you could do. It would take hours, I remember. And what it would do, it would bring all the elements for one file together in one sequential order. And then after that, it would be really cool to see that those colors. Now, each file had its own files all in one place. So it would take really long time, depending on the size of your storage, depending on the kind of processor you are using, because what it does is basically moves storage blocks, and that's pretty expensive to do. But it was necessary, really, back in then, because if you wouldn't do this, your system would get super, super, super slow, because again, all your file blocks were scattered on your magnetic disk. So you wanted to read a file, and then it would just take forever. And then you do a defragmentation, your system would be smelling like new, would be super fast for another 2 months until you have to do another defragmentation again. So that's the disadvantage. No support for hard links. It only supports one link per file, and it's mainly because of the way metadata is stored. Basically, you don't have much metadata stored with your files. Why? Because you have only 32 bits per FAT entry. So there's not much you can store besides, the name of the file and the next entry. And then eventually limited volume and file size. So these are two different things. First of all, how big your storage could be was limited by the fact that you had only few yeah, so if I go back, I think as I said, so each entry is 32 bits, and then 4 bits are reserved. That gives you 28 bits per entry. Now remember that each entry has to point to another entry, right? So what is the maximum number of entries you can address is 2 to 28 entries that you can have in your system. If you have more of that, then you cannot address them using 28 bits, right? So that's the whole point. They're just pointing to each other. So they have pointers to each other. So if you have more than 2 to 28 of them, then some of them cannot address the other ones, right? Or each one of them cannot address all of them. So that restricts you from how many of these elements you can have. And the number of fat entries basically is the number of blocks, storage blocks that you can have. So that's basically a hard limit on how big your volume could be. So with blocks of 4K, the maximum size was 1 terabyte. So more than 1 terabyte, you can't manage the storage device. There is also a limit on file size. Each file can have a maximum of 232-1. So each file can be at most 4 gigabyte. So maximum of volume and maximum file. Well, this is fine if you're using it for an SSD card, but for data center usage, for example, this is not acceptable. Okay. And finally, because you don't have much support for metadata, it's hard to have like access permissions, do anything meaningful when it comes to reliability and security. So they're all off the table. You can't really do much without metadata. So overall, super simple, but not up for serious use cases in today's competing world. Okay, now I'm gonna actually stop here. I'm not gonna talk about further file systems. So if it should be obvious where we're gonna go next, right? The first one was a linked list representation of file blocks. How do you improve that? You use tree, right? That's what Berkeley Unix fast file system did, and that set the stage for all the other modern file systems that came afterwards. So they store data blocks using a tree structure that has dedicated space for metadata. So basically, we saw FAT's disadvantages. We want to fix them. We want to make it faster to find blocks. So that's why we are using tree. We wanted to have metadata. We allocate metadata to it. And in particular, Unix took this to heart that most of files are small. So it made small files really fast. So it dedicated a whole bunch of elements for small files. So to basically manage them really fast. But if you're big file, you're screwed. You have to traverse. So the tree that FSS uses is asymmetric tree. So it's not symmetric. So if you're a small file, it's shallow for you. So the search is really fast. You don't go deep. If you're a big file, then you have to traverse more nodes. And so the access time goes up because you have to traverse more, but it still can support big files, actually huge files. So it could go up to 4 terabyte of data at the the deepest level. It still has limit on how much file it could support. So it can support up to files up to 4 terabyte plus 4 gigabyte plus 4 megabyte plus 48 kilobyte. So orders of 4 terabyte per file, which is pretty good. Compare that to 4 gigabyte for FAT. As I said, it's a asymmetric tree. Yeah, they had a lot of, smart ideas to manage storage so that it's super fast. Because again, another downside of FAT was this fragmentation issue that would lead to having your data scattered over the disk. In FFS, I think I said FSS. In FFS, they did a lot of smart stuff to keep your file local. Unfortunately, I don't have time to talk about them, but they did a pretty, amazing optimizations to make it really fast. There are versions of FFS that fix some of the disadvantages that it had, but again, I won't be having time to talk about them. The next file system that I talked about last term was NTFS, which is basically Windows's Microsoft's improvement on FAT. So FAT was from Microsoft. They improved it with NTFS. And this one is also very interesting. It's also tree, and it's also sort of asymmetric. But again, unfortunately, I won't be having time to talk about it. I will link a video from last term that I talked about all of these. So that's pretty much it. Yeah, unfortunately, I won't be. How much time do I have left? 2 minutes. Okay, so let me just very, very briefly in 2-3 minutes set the stage for reliability for those of you who will end up watching reliability videos. So bottom line, as I described, is that you want your data to persist on your device, and that basically has two things. One, reliability, and second, durability. Now, for durability, to make sure that your data remains even when the device gets corrupted, you usually use a technique called RAID. And the main idea behind RAID is basically make multiple copies of your data. So if it's important for you to have durable data, make multiple copies. If one copy is lost, you have another copy. Now, you can do this very smartly using encodings and smart ways of duplicating your data instead of just duplicate the entire file. Because that's not efficient. You're basically utilizing only 50% of your storage. You can actually increase the utilization by smart ways of storing and duplicating. So that's the main technique for durability. Now, when it comes to reliability, the main technique is using transactions. And basically, yeah, unfortunately, I won't have time to talk more about it, but with transactions, you want to make sure that, again, each file system operation, if it's divided to multiple micro operations, you want all those micro operations to happen or none of them to happen. You don't want some of them to happen and then some other ones not to happen. So that's the main idea. You put all those microtransactions into micro operations in one transaction, and you tell the system, I want the entire transaction to happen or none of it to happen. And then when you have sets of transactions, you want all the transactions to be isolated from each other. So one transaction should not see the result of another transaction until that transaction commits. So it shouldn't be seeing anything in between while the transaction is preparing the data. Should be completely transparent from another transaction. And then if a transaction commits, you want the data to be written to the file system so that it's durable. Anyways, so unfortunately, I didn't get a chance to talk about reliability. I will definitely include a link in the description on YouTube, pointing you to the lectures from last term. Okay, so that's pretty much it. It was a pleasure, really, to teach this this term. It was difficult, 100%. So I have gotten feedback from students. I know we had some hiccups with the labs because of losing the lab instructor, because of the device, the lack of hardware devices, and I mean, I have to take responsibility also for those, but I did what I could. So thank you, everyone, for your hard work. Again, I hope you learned something important that you could build on top of it in your careers. So again, thank you so much. Take care, be safe, and maybe talk to you in another course. So let me actually tell you, I'm teaching game theoretic foundations of multi-agent systems. It's completely different from this operating system course. So it's kind of like a theory course in next winter, I believe, in winter 20. Let me see. Yeah, winter 22, I believe. So basically next year, the exact term, this term next year, I'll be teaching that course. It's a course for graduate and undergraduate sections, so it has both. So if any of you are interested in multi-agent systems, definitely consider taking that course. So maybe I see some of you in that course next year. It's for fourth year students. It's an elective. Anyways, take care, be safe, and we'll be in touch, I think, for doing lab 4 demos and the last quiz. Bye-bye. Thank you.